Hello, everybody. Today's lesson, we are focusing on conclusions and valid arguments. And this, again, is a step towards geometric proofs. So understanding how to draw correct conclusions, valid conclusions, create valid arguments is all going to be very important. Here's a little warm-up. I'll go if you'll go. Determine who is going to the game. Ben, Al, Carla, Dawn, or Eva. Now, if you're watching this video, I would pause it right now. I would read the 5 statements and then answer the 5 questions on your own. Then start the video again and see how you did. Statement 1. If Dawn is going, then Eva is going. Statement 2. Ben is not going to the game. 3. If Al is going, then Ben is going. 4. If Carla is going, then Dawn is going. And finally, Al or Carla is going to the game. Now let's answer the 5 questions. Question 1. Is Ben going to the game? Well, we can look up above at statement 2, and it states very clearly Ben is not going to the game. So we know that no, Ben is not going to the game because of clue number 2. Question number 2. Is Al going to the game? Looking at the clues above, clue number 3 says if Al is going, then Ben is going. Now we know that Ben is not going. So therefore, Al cannot be going either, because if he was, Ben would have to be going. So we know the answer to number 2 is no, Al is not going to the game. And we know that because of clues 3 and 2. Question number 3, is Carla going to the game? Clue number 5 up above says Al or Carla is going to the game. This is a disjunction. We know that a disjunction is true when one or the other or both are true. Now we already know that Al is not going to the game. Therefore, Carla must be going to the game for clue number 5 to be true. Therefore, yes, Carla is going to the game. Question number 4, is Dawn going to the game? Well, clue number 4 gives us the answer. If Carla is going, then Dawn is going. And we already know that Carla is going, therefore, yes, Dawn is going. And finally, question number 5, is Eva going to the game? And clue number 1 up above says that if Dawn is going, then Eva is going. So therefore, yes, Eva is going to the game. This warm-up helps us apply our understanding of both conjunctions, disjunctions, conditional statements, and negations. All right, moving on. We introduce a few more vocabulary terms. First, the premise. The premise is a given statement in an argument. The conclusion, a statement resulting from the premise of a logical argument. And finally, a valid argument, an argument that uses rules of logic. Let me remind you that the expectation is that you are taking notes during this lesson. So if you need to pause the video and write these definitions down, do so. Next, we're going to introduce our rules of logic. The first rule of logic is called the direct argument. And it goes something like this. If P is true, then Q is true. P is true. Therefore, Q is true. The 3 bullets that you see here on the left form the direct argument. We can represent the direct argument as a Venn diagram. Notice in our Venn diagram that circle P is inside of circle Q. When P is true, we are inside of circle Q, which means Q is also true. And then finally, the notation over on the right. If P, then Q is represented by this first statement. Next, we state P, meaning P is true. And finally, our conclusion. Therefore, Q. The English words that you see here in the bullets and the notation that you see over here are the same. Our next rule of logic is called the indirect argument, and it states, if P is true, then Q is true. Q is not true. Therefore, P is not true. Let's look at the Venn diagram. If Q is not true, then we cannot be anywhere inside of the Q circle, which makes it impossible to be inside of the P circle. Therefore, we conclude that P is not true. Writing the indirect argument in notation looks like this. If P, then Q. Not Q. Therefore, not P. Continuing on, the next rule of logic is called the chain rule. It states, if P is true, then Q is true. If Q is true, then R is true. Therefore, we can conclude, if P is true, then R is true. Looking at the Venn diagram, we can represent the chain rule with the three circles for R, Q, and P. P is inside of Q and R. Q is inside of R. If P is true, that means that we are somewhere inside of the P circle. While that red dot is also inside of the Q circle and inside of the R circle. So we can conclude that if P is true, then R is true. You can see the notation of the argument on the right. If P is Q, if P, then Q. If Q, then R. Therefore, if P, then R. And our last rule of logic, the OR rule. P is true or Q is true. P is not true. Therefore, Q is true. This goes back to our definition of a disjunction. We know that one or the other thing or both things could be true. But for a disjunction statement or an OR statement to be true, we need at least one thing to be true. So, if P is not true, then we are not inside of the P circle, but we still must be inside of the Q circle in order for the statement to be true. Written in notation, we can see P or Q. That's our disjunction. Not P, therefore Q. So now let's put these rules of logic to use. Identify the rule and state the valid conclusion. John is in his room or in the kitchen. John is not in the kitchen. So we conclude that John is in his room. This is using the OR rule. Number 2, if I take the number 10 bus, then I can get to the mall. If I can get to the mall, then I can go to the movies. So we conclude, therefore, if I take the number 10 bus, I can go to the movies. This is the use of the chain rule. And finally, number 3. If Kelly is tired, then she is cranky. Kelly is not cranky. Therefore, Kelly is not tired. This is the use of the indirect argument. Now, if you're reading these saying, hey, these make sense to me, these are easy, well, that's simply because you've applied good logic throughout your life. Next, we're going to apply our rules of logic to recognizing invalid arguments. It's going to be very important then when trying to recognize invalid arguments that you simply try to apply the rules of logic. If a rule of logic is applied, then it's a valid argument. If a rule of logic is not applied, then it's an invalid argument. Let's look at some examples. If a number is a multiple of 20, then it is a multiple of 5. Sam's locker number is a multiple of 5. Therefore, Sam's locker number is a multiple of 20. Now be careful you don't fall into the very common trap of trying to calculate this mathematically. We want to represent this argument symbolically. The first statement, if a number is a multiple of 20, then it is a multiple of 5. That's an if-then conditional statement. We can call this P and this Q. And we can rewrite this if P then Q. The second statement, Sam's locker number is a multiple of 5, is the Q statement. Notice, is a multiple of 5 and is a multiple of 5. Those are saying the same thing. So, the second statement is Q. The third statement, therefore Sam's locker is a multiple of 20, well, that's statement P, right? Is a multiple of 20 and is a multiple of 20. So, our third statement says, therefore P. Now the question is this one of the rules of logic? Think back, the direct argument, the indirect argument, the OR rule, and the chain rule. Well, in fact, this is not one of the rules of logic. So this is an invalid argument. Although this notation looks like the direct rule, the direct argument, remember that the direct argument says, if P then Q, P, therefore Q. You can see how this has been switched around, the P's and the Q's. Therefore, it's not the direct argument. It is not any rule of logic, and therefore is an invalid argument. Here's a second one. If x equals 5, then 2x plus 3 equals 13. 2x plus 3 does not equal 13. Therefore, x does not equal 5. Now again, don't fall into the trap of trying to solve this mathematically. Let's solve it by applying the rules of logic. First, we rewrite the argument symbolically. If P, then Q. The next statement says 2x plus 3 does not equal 13. Well, remember our statement Q says 2x plus 3 does equal 13. So our next statement is actually the negation of Q. Therefore, x does not equal 5. Well, statement P said x does equal 5. Now we're saying it does not equal 5. So we write, therefore, not P. Now ask yourself, is this one of the rules of logic? The answer is yes, it is. This is the indirect argument. Therefore, this is a valid argument.